introduced in version 1 of their header format, which they've discarded again in version 2, is loosely based around a standard that is commonly referred to as PKCS7, which is RFC 2630. And what is kind of funny about this is they wanted to implement it with a random IV that they store on the drive, and they actually do store this IV on the drive, but they don't actually use it. So it looks like somebody, started an implementation and, got held up and didn't quite finish, and then they ditched it and went to another header format. But all that stuff is open source. The reverse engineering was just the disk images framework. Okay, now to the recovery mechanism. When you enable file vault, you can, or basically you have to set a master password. This master password, in turn, protects a keychain that is in your library keychains directory. And this recovery keychain, it's called, contains one certificate and one private key. And this private key is a 1024-bit RSA key. By having this key, you can decrypt another struct in the metadata that also contains the blob where the encryption password and the HMAC password for decrypting the real data that's in your file vault images is contained. Now, the problem is there's something called the Lenstra-Verheul heuristic. And what this does is basically it establishes a mapping between the parameter sizes of symmetric and asymmetric key cryptography. And, well, Apple claims they have 128-bit security, but this, if you have set a master password, is not quite true. Because by having set a master password, you have this 1024-bit key on your drive, which is, this key is not encrypted, right? I mean, it's sitting out in the plain text. I should add, like, file vault is only protecting your home folder. It's not protecting all of the other folders on your file system. Now, 1024 bits asymmetrically, according to Lenstra-Verheul heuristic, means 72 bits symmetrically. That's not a lot. Usually, these days, you should have at least 80. Okay, so that we went into already. The headers of version 1 live at the beginning of the file, and the version 2 headers live at the end. And in 10.4.7, they actually made the version 2 headers mandatory for sparse encrypted disk images. That's probably because when you log out, the disk images get compacted. Now, if you think about what happens if you compact a disk image, it shrinks, right? And you have the metadata at the end, and you have a power failure, for instance. Where's your metadata after that? Well, whoops, gone. So that's why you should have it like in the new format. Now, let's look at the gory details. The password header, in principle, is very, very generic. I mean, they could easily swap out the key derivation algorithm. They could swap out the PRNG algorithm that they use for generating temporal keys when you re-encrypt, for instance. They could have different algorithms for the symmetric encryption of the blocks. They could have different modes. They could have different paddings. But they don't actually use that. They just have one C-encrypted encoding. And that is, I mean, that statically is AES-128. That's kind of interesting, I think. I'm not sure what future versions of OS X have planned. But what I'd really like to see is Apple opening up the disk images framework and allowing other people to write plugins for it, because then you could theoretically also mount disk images, or rather loopback devices in the form of disk images from other operating systems, so you could have actual interoperability, something that's kind of missing in the market of disk encryption these days. I mean, there's TrueCrypt, which is cross-platform, but it doesn't run on OS X. And then there's PGP Disk, which runs on basically everything, including OS X, but it's not open source, really. So go to the next slide, please. Reversing the disk images framework was actually quite easy, because disk images is C++ code, and when you look at the binaries, you can extract like the full signatures of every method of a class if it's not obfuscated, and Apple has not obfuscated disk images. So all of the analysis basically was done using like OTool, GDB, and the debug output of HDIUtil. HDIUtil, I should add, has a little debug switch, which is great because when you turn it on, it gives you all of the internal, it gives you all of the internal steps it has done. It outputs you the HMAC SHA-1 key, it outputs you the encryption key, so you can verify that you've actually done the right thing when you've reverse engineered and have written your own implementation. Initially, I thought it might have been easier to reverse engineer disk image framework using something called Boomerang, which is a great reverse compiler, but unfortunately, although it supports Macho, the Macho binary format, which is the default on OS X, it doesn't really work so well with PowerPC code, and after I patched it to work with Intel code, it worked better, but it like bombed out on me in like 3/4 of the cases, so it wasn't really useful for generating more than like 1 or 2 functions from the binary. So, but actually, if you look at the disassembly, if you look at the PowerPC disassembly, it's not that hard to see what's going on, because the calls that they make to the CDSA framework are very similar in structure. So once you've figured out one of the calls, you get the hang for the rest of them. You just have to be careful because you have to follow a lot of pointers to the structures, and on OS X right now there are, as I'm aware of, no good reverse engineering tools. There's IDA Pro for Windows, but you can't really use something. There's no similar thing such as IDA Pro on the OS X platform. Now, the results that we have is we have something called while fault decrypt. Actually, that's a spelling mistake on the slide. It should be a V and an F instead of an F and a V. What it does, you feed it an encrypted d-image, either like a sparse d-image or a non-sparse, like UDIF d-image, and it outputs you the decrypted d-image if you have the correct passphrase. This tool works with both version 1 and version 2 encrypted disk images, so even if you have like an old installation and you want to like transfer your data off that, but you don't have the install media, but another box which runs an open system, you can still get the data off it if you have the passphrase or if you can guess it. What it doesn't do is it doesn't expand the sparse images to a real disk image. This is kind of a problem still, because what that means is if you have a sparse disk image, you can't mount that, say, on the Linux, because although Linux has support for HFS and HFS+, well, it doesn't know how to use sparse images. So what's needed here is like another converter that converts these sparse images to full-blown images that can be mounted. But that is fairly trivial from what I've seen. The code is very rough at the moment. For instance, it doesn't do the recovery thing yet, but we're working on that still. The code works, and it will only get better. What we also showed is that the cryptography of file vault does not only depend on AES-128, I'll reiterate that again to make the point, but it also depends on triple DES, which effectively has only a bit, an effective key length of 112 bits, and on the security of RSA-124. So if either of these three folds, you're screwed. The other thing that's bugging us about file vault is that we'd actually like to have full disk encryption, not just the home directory, because there are a lot of applications that spit all over your file system, like into temp, most often. But also have a look around what you leave behind in var log or in system logs, and then think about, well, if you do something compromising, I'm not sure how many people are in the audience that are, extra legally active. Yeah, basically, you might put information into areas of your disks where the police or other agencies can find them if they seize your laptop, and that's not such a good thing for you. So we'd like to have the full disk encrypted. This actually is possible using the Disk Images Framework because it has the CDF backing store, which allows you not to have a file as the container, but a whole device. Unfortunately, it looks like it's not possible using just the HDI util, so you have to hack something up that makes use of the framework by generating headers for yourself, or you have to wait for Apple to do that for you. So maybe the next version has support for full disk images. I've heard that it has recently become a requirement in, maybe Jacob can say something about that?
So I guess recently there's been a presidential mandate this summer from our glorious leader about full disk encryption for all federal government computers. So this could be something that potentially would be a big market for Apple if they were to fix this and open it up. Maybe. It's possible.
Okay. Another thing that you have to look at when you look at any kind of cryptography, obviously, is you have to look where your randomness comes from. Now, with OS X, it's kind of funny, because OS X uses a very well-known and very reputed random number generator called Yarrow, but they heavily modified it. What this means is, usually in other operating systems, you have the kernel collecting entropy throughout the course of the day from various sources, like from interrupt activity, from the number of pages you swap in and swap out. Oftentimes you actually have a hardware number generator. Newer Intel Macs have, or all of the Intel Macs have hardware number generators in the CPU. But from what it looks like, the implementation that they've chosen doesn't utilize any of that. It just gets the entropy from the system time. And how they do this is kind of backwards, because they have a security server, that's what it's called, running in the user space, which feeds entropy to the kernel by writing to dev random. Now, this security server, in turn, gets this entropy from where? Oh, the kernel. And they do that through a debug interface, which is, I think, kind of funny. They do that every 15 seconds. So I'm not saying that that this design can be broken easily. I actually think it's quite hard to come up with a practical attack against it. But I still think it's not very beautiful, and you'd have to think hard about it to justify it, actually. I'd actually like a reason why they did that. And The other thing is that receipts are done.